So today we're going to talk more about functions and their derivatives and inflection points and extrema and all of that again, okay? Just the information that's going to be presented is going to be slightly different than what we've been seeing, okay? So here we go. Function f is continuous on the domain, -2 to 4. So that means the function has no breaks, okay? We know that f of -2 is 5, f of 4 is 1, and then we have this information about f prime and f double prime. They have the following properties. Now, what this is a sign chart, okay? So this is the interval -2 to 0. So that would be this, -2, comma 0. This is exactly 0, what's happening. This is the interval 0 to 2. This is x equals 2. So that's exactly, so the derivative is 0 at x equals 2. And 2 to 4, that tells me something about the derivatives, okay? All right, and so we know because the first derivative is 0 at x equals 2, we're going to have a horizontal tangent there. We're going to be increasing on this interval. We're going to be decreasing, and then we're going to continue to decrease from 2 to 4. So we're actually decreasing from 0 to 4, okay? So the concavity, all right, second derivative, concave up here because the second derivative is positive on this interval, okay? And actually, it would be concave up for the entire time from -2 to 2, looking at this, and then concave down on this interval, okay? So here's the first question. Find where all relative and absolute extrema of f occur. So let's start with the relative, okay? So we're looking at the first derivative, and we're looking to see if it changes from positive to negative or negative to positive. And if we look on this interval, it's positive, and this interval, it's negative. So yes, it changed signs between these. So it's changing at x equals 0, okay? And then it's not changing because it's negative here and negative here. So we have a relative, so f would have a relative. F has a relative. And what is it? Because we're going from positive to negative. So that means we're going from increasing to decreasing. So we have a relative maximum at x equals 0 because f prime changes from positive to negative at x equals 0. And that's the only one, okay? Now, absolute maximums, okay? So this is a closed interval. So I would normally say the closed interval test, and we would need to find f of -2, which we have, f of 4, which we have, but there's no way to get f of 0 or actually f of 0 because that would be a critical value, okay? And f of 2, okay? Both of those would be critical values because the derivative doesn't exist, or that means it's undefined. And here the derivative is 0, okay? But there's no way to get the values here. So we have to go about this a different way, okay? We have to think about the behavior and what the derivative is telling us. So what this is telling us is we start and we're from -2 to 0, we're going up, we're increasing, but then we start to decrease. Starting at 0, we start to decrease, and then we decrease again. So if you're going up, okay, and then coming back down the rest of the time, this at x equals 0 would have to be the absolute biggest value for f, because think about it, we're increasing and then we're decreasing the rest of the time. That's the highest it gets. So we have an absolute maximum at x equals 0. So f has an absolute maximum at x equals 0, okay? And then at for an absolute minimum, and we're guaranteed to have one, right? What we have to know, did we go down? Okay, so we went up, we started here, all right, and we started at f of -2 is 5, that's an endpoint, right? And f of 4 is an endpoint. So we went up, and then we started to go down, okay? How far did we go down? Well, we went down to 1, right? We started at 5 for a y value, and we went up and then we went down, but we went all the way down to 1. So this one has to be our absolute min. Now you may be wondering, well, why can't the absolute min happen at x equals 2? Well, because it's decreasing and then it's decreasing. So any point in this interval is going to be smaller than this one, all right? So f has an absolute minimum at x equals 4. So we had to use a little bit of reasoning and understanding of what the first derivative is telling us in order to determine these two, okay? If we were given the function, then we could just plug in f of -2, f of 0, f of 2, and f of 4, and then go ahead and see which one's the biggest and which one's the smallest, but we weren't able to do that, okay? So here's one more thing, okay? Find where the points of inflection of f occur. So that's going to be where the f double prime is changing signs. So in this interval, it's positive, okay? And then this interval, it's positive, and then this interval, it's negative. And this was a critical value, right? And so it changed from positive to negative. So f has a point of inflection at x equals 2. So we'd say f has a point of inflection at x equals 2 because f double prime changes signs at x equals 2. Okay, so now the next step is trying to figure out, we're going to sketch a possible graph of f, okay? So let's start by plotting the two endpoints. So we know f of -2 is 5, so that'd be right here. And that's my left endpoint. And I know f of 4 is equal to 1. So f of 4 is equal to 1. That'd be right here. And so we're going to have to get from here to here, but we're going to have to graph it so that all of these fit, okay? So we know at x equals 0, right? At x equals 0, we have a relative maximum, and it's also the absolute maximum. So at x equals 0, we got to draw a point that's higher than all the others, okay? So let's draw it way up here. It just has to be higher than these two, okay? That's all that has to happen, okay? So what we have to draw is from -2 to 0, okay? We have to draw it so it's increasing, okay? Because that kind of makes sense just where I put that. And we have to be concave up, okay? So we have to draw it. So it could be, and then we don't have a derivative at x equals 0. So right here, there has to be a corner or a cusp, okay? Or something like that. Something that there's something there that's causing us to not be able to take the derivative, okay? And then we have an inflection point at x equals 2, so it's going to change concavity somewhere in here, okay? And we're decreasing the entire time from 0. So I'm going to put a point right here. Let's put it right about here, okay? It really doesn't matter where you put this, okay? All right, so let's start drawing this, okay? So we know we're increasing concave up, so that could be something like that. So it's got to bend up, okay? I missed my point right there a little bit. All right, and then from 0 to 2, okay, we got to be decreasing, but still concave up, all right? So that could look, and I should say this, right at x equals 2, we have a horizontal tangent. So I should draw it horizontal right there, okay? So again, we can't take the derivative here, and we need to be negative, so we're decreasing. That makes sense to get from this point to this point, and we have to be concave up. So that could look, something like that, okay? And so just double check, okay, yes, it's decreasing and it's concave up. That meets all of that, okay? And then right here from 2 to 4, we got to be decreasing, but this time we got to be concave down, right? And so we're going to come off this and we're going to bend it so it's curving down, and we've got to get to this point. So that's all that has to happen, okay? So we've got to get to this and definitely be curving down, which we are, okay? So your graph should look something like this. Now where this point is, it just has to be higher, and where this point is, it just needs, this point right here needs to be in between wherever you put this one and this right endpoint, and that's all, okay? So this, basically this left endpoint, or sorry, this point right here has to be above 5. That's it. That's the only restriction. And then 2 at x equals 2, this point right here has to be somewhere between 1 and wherever you put this point, and you have to have a horizontal tangent there, and the concavity and the increasing decreasing all have to fit. Okay? So for this next example, the function f is continuous on the closed interval -4 to 4, and the discontinuous function f prime with domain, and here's the domain, there's a break at 0 and a break at 2, and that's what this is showing. And remember, this is the graph of f prime, okay? So graph of f prime. So the graphs of the derivatives will tell us stuff about the function, okay? And where it's increasing, where it's decreasing, where there's relative max, relative mins. It will also tell us the concavity, all right? So it's telling us, just the graph of f prime tells us everything, all right? So find the x-coordinates of all local extrema and points of infections. Not infection, inflection. Sorry. Too much COVID-19, huh? Sorry. Bad joke. All right. X-coordinates of all local extrema. So, all right. So we're looking for where the derivative is 0 or undefined, and we're looking to see if f prime changes from being positive to negative or negative to positive, okay? So I'm just gonna go left to right, okay? So from left to right, the derivative, because this is on the x-axis and the value would be 0 right here at -3, okay? And just before that, the derivative is positive, and just after that, the derivative is negative. So we're going from positive to negative, which tells us that you have to have a relative maximum at x equals -3. So we'd say f has a relative maximum at x equals -3 because f prime changes from positive to negative at x equals -3. And I'm going to tell you, I'm going to do a separate sentence for each one of these, okay? So now the derivative is negative, and now the derivative at -1 is 0, and then the derivative is positive. So that the derivative is changing from being negative to positive at x equals -1. So that would tell us that if we're changing from negative to positive, we have a relative minimum right there. So f has a relative, or local, you could say local too, relative minimum at x equals -1 because f prime changes. And the way it changes matters because that dictates whether it's a local or relative minimum or max. Changes from negative to positive at x equals -1. Okay, so the next thing that's happening is the derivative is undefined, okay, or doesn't exist at x equals 0. And just to the left of that, the derivative is positive, and just to the right of that, the derivative is negative. So the derivative is changing from being positive to being negative at x equals 0. So when it changes from positive to negative, that would mean f has a relative maximum. So f has a relative maximum at x equals 0 because f prime changes from positive to negative at x equals 0. Okay. And then what happens next is the derivative is negative and then the derivative is positive. So there's another relative extreme right here at x equals 1. And because it was negative, that means it would decrease. The function's decreasing and then increasing. Then that's telling you it's a relative minimum at x equals 1. Okay. So f has a relative minimum at x equals 1 because f prime changes from negative to positive at x equals 1. Okay. And then we have another one at x equals 2 because the derivative doesn't exist right there. Okay. And so just before 2, it was positive, and just after 2, it's negative. So f has a relative, and this would be because it's changing from being positive to being negative. So that means increasing to decreasing. We have a relative maximum at x equals 2 because f prime changes from positive to negative. And I just realized you can't see it. So it changes from positive to negative at x equals 2. Okay, and then inflection points, right? So inflection points. So that'd be the second derivative, all right? And the second derivative is the first derivative of the first derivative, okay? So, and then the derivative is slope. So we're looking at the slope and where it's changing, right? Or in other words, where this graph is changing from either increasing to decreasing or decreasing to increasing, all right? So f prime right here at x equals negative 2 is changing from decreasing to increasing, or the derivatives of this are changing from negative to positive, and the derivatives of this are actually the second derivatives of f. Okay, hopefully that makes sense. All right, so we have f has an inflection point at x equals negative 2. So f has an inflection point at x equals 2. And the way we know that is because, and we have to refer back to what the stem of the question, and the stem deals with f prime, okay? So f has a point of inflection x equals 2 because f prime changes from increasing to decreasing at x equals, and you know what? I said 2 and I meant negative 2. I wrote 2 right here and I meant negative 2. Okay. Now, what about at 0? Well, it's changing from increasing to increasing, right? So that's not an inflection point. And then here it's increasing. Okay, so here it's not decreasing and it's not also not increasing, right? It's not doing either one. So actually that's the only point of inflection. It's happening at x equals negative 2. All right, so what I want to do next is I want to take all the information we have and we want to graph it, okay? A possible sketch of this, okay? Now, a couple things I would start out doing is look for where the derivative is 0, which means we have horizontal tangents, okay? So at x equals negative 3, we have, it went from positive to negative, so that's a relative maximum. Okay, so I'm gonna need to put that one a little bit high on the graph here, okay? Because we don't know any values, right? So we just gotta do in relation to other points, okay? So we have a horizontal tangent at x equals negative 3. So I'm gonna put that like right here, and I'm going to draw a little horizontal line right here. okay? And also at x equals -1, we have a relative minimum right there, okay? So I'm going to draw this one. I'm going to draw it right here, okay? And I know I'm going to have to come in and be horizontal right there, okay? And then at x equals 0, we're going to have a corner or a cusp. Because we know it's continuous, right? So there's no break. So it's not a discontinuity that's causing the function to not have a derivative. It's a corner or a cusp, okay? And then same thing is happening at 2. So right here at 2, we have a corner / cusp, okay? It can't be a discontinuity because we know it's that function is continuous and we're graphing the f, all right? And then we also know we have an inflection point at x equals -2, right? So what I would, and we know it's decreasing here, so we have to draw it so that it's concave down, okay? So from -4 to -2, we have to draw so it's concave down, okay? So I would draw something like I'm thinking like a parabola-ish, okay? I'm going to come up and then down. And then right here, I'm going to draw it. So this is coming up and meeting that, okay? And I'm trying to kind of show that it's really hard to draw an inflection point. Same thing that we talked about the other day, all right? That it's really hard to, yesterday, right, lesson, it's really hard to find it and pinpoint it, right? So it's going to be hard to draw it too and show it. So then right here, okay, so we know this is increasing and it's concave up because here the derivative is increasing, here the derivative is positive, so I have to be increasing concave up on this interval, okay? So I would just think about like a parabola shaped looking thing that comes up like that, okay? Now I gotta quickly change right here directions, right? Okay, and then what's happening at x equals 1? At x equals 1, we're changing, and we have a, you know what? I forgot to draw this. We have a horizontal tangent at x equals 1 too, all right? And just before that, just before 1, we're decreasing. So heck, let's just draw it right here, okay? Right there, okay? So I would come up, you know, something like this. We know this is increasing, so it has to be concave up, all right? But decreasing from 0 to 1, we have to be decreasing, but we have to be bending up. So perfect example would be something that looks like, you know, parabola-ish again, okay? And so right there, definitely can't take the derivative, okay? And then right here, I want to wind up right here, okay? And so this needs to be right here. Hold on, I take that back. I'm increasing right here. So I have to actually come back up, right? And I have to still be concave up. So I can't actually, I take that back. I can't put it right here. I'm gonna have to put it right here. All right, so once again, between 1 and 2, all right, the derivative is above. So that tells me I have to be increasing. And if I was down here, I'd have to decrease, okay? And then also this graph is increasing, which tells me it's concave up. Okay, so I have to draw it so something like this. Okay, and then we don't have a derivative at 2, so it's corner cusp right there at x equals 2. Now this is very specific right here. This is telling me the slope is -2. So I wanted to end this point right here at a nice coordinate because after this, from 2 to 4, the slope is going to have to be -2 because this is a constant, right? The derivative is constantly -2, which means the slope of your graph has to be -2. So I'm going to come down 1, 2, and write 1. So right there. And I just lucked out. I'm going to end right here, right? So down 2 and write 1. Okay. And then I'm going to grab a ruler and I'm going to connect these points. Okay, so from 2 to 4, the derivative is going to have to be or the function is going to have to be a straight line. Okay. So you have to draw something that looks like this in order to meet everything. Okay. So not differentiable right here, not differentiable right here. Concave down, horizontal tangent right here, horizontal tangent right here, concave up, horizontal tangent right here, decreasing. That kind of makes sense. We have to go from here to here, okay? And then corner cusps right here, okay? And then slope of -2 from here on out, okay? All right, so you guys, that's how you do graphs like this, okay? So I'm gonna provide some graph paper that you're gonna maybe, if you can't print it, you're gonna have to sketch it yourself, okay? And I would just use graph paper. You're just gonna have to draw in this, just take my PDF, okay? And you can just draw the same scaling, all right? Something else that I need to talk to you guys about that you're gonna see on homework, okay? On homework, okay, you're gonna see them describe intervals like this. The absolute value of X is less than or equal to something like, let's say 5. Okay, so we're gonna have to interpret this, okay? That means all the distances that are less than 5. So what this means, okay, is that we're talking about all the numbers that are between -5 and 5. So this translates into -5 is less than or equal to X, which is less than or equal to 5. Okay, so you're gonna need that. So this is talking about all the numbers, all the X values between -5 and 5, okay? So if you saw something like this, absolute value of X is greater than or equal to 5, that would be describing the numbers where X is less than or equal to -5, or X being greater than or equal to +5. Okay, so this one's in between -5 and 5, and this one's to the left of -5 and to the right of +5, and that's what this is saying. Okay, I don't think this comes up, but I just wanted to go over it with you. It's good math. All right. All right, you guys, short lesson today. All right. You guys have a great day.